Hello everyone, my name is Harpreet. I'm a PhD student at Texas A&M and today I'll be presenting our work, Adaptive and Efficient Dynamic Memory Management for Hardware Enclaves. This is a combined effort of researchers from Intel, UNC Chapel Hill, Texas A&M, and Virginia Tech. The work focuses on discussing the pitfalls of dynamic memory management in Intel Software Guard Extensions, or SGX, and how we optimize it to reach closer to the performance of static allocation while maintaining the flexibility of demand paging. Let's start with understanding the overall framework of Intel SGX. If an application has sensitive code and data, it needs to be isolated from not only the rest of the application but also from other processes and the kernel. Intel SGX isolates the sensitive code and data of an application inside a sandbox called an enclave. An enclave relies on the hardware, in this case a SGX supporting Intel CPU, to encrypt its physical pages and thereby helping isolate its context. Intel SGX protects the confidentiality and the integrity of sensitive code and data through isolation and encryption. Initial versions of SGX allocate memory through static allocation. All the memory of an enclave gets allocated at enclave initialization. All the virtual pages pertaining to an enclave are mapped to physical pages, which reside inside a page cache called Enclave Page Cache or EPC. This EPC holds all the encrypted pages in such a way that the pages are accessible only from an enclave, but neither the untrusted runtime nor the kernel. Because all the pages need to be allocated at the same time, the time for loading increases drastically. For example, it can take around 15 seconds to load an enclave of 2 gig heap size. This can be a significant concern in modern day due to omnipresent cloud applications. To deal with the high overheads of loading an enclave, Intel SGX introduced a subsequent follow-up version with Enclave Dynamic Memory Management, or EDMM, to be able to have smaller heap sizes at enclave load time. New pages can be mapped on demand if needed in the future. Suppose an application wants to read from or write to an address on an unmapped virtual page. The attempt leads to a page fault on the page. This page fault transfers control to a unit called a SGX driver, which dependent on the kernel version can be in kernel or out of tree. This eventually leads to an EOG operation, which is a new x86 instruction introduced to map new enclave pages. Note that the page is not yet available for use by the enclave. In order for that to happen, control flows back to the exception handler in the untrusted runtime. The untrusted runtime facilitates re-entry into the enclave using SGX API, leading to eAccept. eAccept is another new x86 instruction added in SGX version 2 to finally acknowledge the new mapping and making the page securely available to the enclave. eAccept is security critical because in SGX, the enclave cannot trust the kernel and has to verify the pages on its own. At this point, the control is transferred back to the untrusted runtime, which finally loads the correct context needed to resume execution from the faulting instruction. Given this flow, we can see that although there is added flexibility to memory management, there are too many context switches. And this, just by intuition, should add significant performance overheads. Exactly how bad it is, we'll soon see in the results. We run our experiments on a 272-core Intel Platinum CPU machine with a 108 MB L3 cache, 248 gigs memory with approximately 4 gigs of EPC available. The hard drive is a 500 gig SSD, and we use a Linux 6.7 kernel, which has an in-kernel SGX driver. We run rbench and gcbench on Grameen SGX. We use Grameen Library OS modified to run with SGX to evaluate the performance of the applications. A library OS allows unmodified applications to be run inside an enclave while providing interceptions for expensive operations like syscalls and I/O, such that the application doesn't need to exit the enclave for every one of them and further expose itself to untrusted entities like the kernel. Demand allocation affects the performance of different applications based on the enclave size requirements and the number of faults an application might incur during its execution. Our bench shows high overheads for loading an enclave when statically allocated, as it requires large enclaves to run, around 2 gigs for our experiments. Although with demand allocation, the load time reduces significantly, thereby lowering the time of total execution for the application, the runtime is still high. With GC Bench, for which we allocate an enclave of 512 MB, we see a significant adverse impact of demand allocation. Demand allocation is penalizing applications with small heap sizes but more frequent accesses. As we can see, EDMM isn't free. Then what can be a better strategy? Can we get the best of both worlds where we have the flexibility of demand allocation while achieving a performance closer to static allocation? To this end, we present our optimizations to EDMM, again built on Grameen SGX, to help lower the overheads of demand paging in SGX enclaves. In this presentation, we'll go over pre-allocation and contiguous demand allocation. Please refer to the paper for details of all the four techniques and the corresponding results. Let's start with the first optimization, that is pre-allocation. In pre-allocation, the number of pages to be allocated and mapped at enclave initialization can be decided at the time of initial configuration. Say we pre-allocate up to X MB. The rest of the pages from the unmapped heap are mapped on demand by the application. The optimal size of a pre-allocated heap is a matter of finding the right balance between static allocation and demand allocation. One of the key flaws of demand allocation was mapping a single page at a time whenever an access to memory led to a fault. In our optimization to demand allocation, we allocate multiple pages at the same time in a technique called contiguous demand allocation or pre-faulting. The complexity of how SCX operates makes this task non-trivial due to the interactions required between the kernel and the untrusted runtime, and the interactions between the untrusted runtime and the enclave through SGX API. Also, an enclave is responsible for guaranteeing the sanity of the pages that it accepts. Whenever there is an access to an address on a page that has not yet been mapped, there will be a page fault. This page fault will subsequently execute the newly introduced SGX version 2 instruction for page mapping, namely eog, inside the in-kernel driver to map the faulting page to a physical page, which will reside in the EPC. Let's say that virtual page is labeled X. On iret, the control transfers to the untrusted exception handler. Rather than returning into the enclave at this point, as was the case with single-page demand allocation of EDMM, our modified runtime will instead perform a syscall to allocate the neighboring n-1 pages using eog. Thus, multiple neighboring pages of the page X will have their mappings in the EPC. On returning from the syscall, there's a re-entry into the enclave where all the n mappings are E-accepted. After accepting the pages, the current context of the enclave is reloaded, and the application can now safely perform the read-write operation on the previously faulting address. Thus, with the cost of one demand allocation, we map up to n number of pages. As previously seen, Demand allocation with EDMM added significant runtime overheads to GC bench execution runtime. But pre-allocating a certain amount of memory shows improvements, especially with a pre-allocation size of 128 MB. In fact, GC bench shows a better total runtime with pre-allocated memory of 128 MB than static allocation. This suggests that GC bench doesn't fall too often if allowed an initial allocation of 128 MB. Even if you use a pre-allocated memory of 64 MB, contiguous demand allocation for 8 and 64 pages shows approximately 5 to 10% improvement on demand allocation and demand allocation with 64 MB with pre-allocated. To summarize, application-specific pre-allocation and demand allocating multiple pages improves performance. Through this work, we want to emphasize that dynamic memory management doesn't always improve performance. It depends on the system flow. In order to optimize EDMM and reduce or in some cases eliminate EDMM overheads, we suggest stacking optimizations like pre-allocation, batch allocation, contiguous demand allocation, and lazy-free together. I'm Harpreet Singh Chawla, and this is my email ID if you have any questions. Also, you can view the grounding code on the GitHub page. Thank